Welcome, everyone. Today, we're diving into ensemble tree models, a powerful method for improving the performance and stability of decision trees. Let's get started. Decision trees can be sensitive to changes in data. Small variations can result in drastically different trees and outcomes. A single tree can also overfit, limiting its effectiveness. Ensemble tree models address these issues by combining multiple single tree models into a collective ensemble. This approach can produce more stable and accurate predictions by reducing variation in prediction errors. With this approach, weak individual trees or weak learners are combined to create a stronger overall model. For classification tasks, ensemble models use the majority rule, where the most frequently predicted class among single tree models becomes the final classification. For predictions, the ensemble takes the average of the individual tree predictions. Some advanced techniques assign more weight to better performing trees, further improving accuracy. Unlike single trees, ensembles cannot be displayed visually as multiple trees are used. This also eliminates the need for pruning. Instead, the data is split into training and validation sets, maximizing the amount of data used for training without requiring a test set. There are three main strategies for creating ensemble models: bagging, boosting, and random forests. Let's break these down. Bagging or bootstrap aggregation improves stability by combining the results of trees built from different training datasets. These training sets are created by repeatedly sampling the original data with replacement. Each sampled set constructs a tree, and the predictions of these trees are averaged. Every case in the data has an equal chance of being included in a sample. Bagging is easy to implement, computationally efficient, and allows trees to be developed in parallel. Boosting also uses repeated sampling with replacement, but takes an iterative and sequential approach. It emphasizes cases that are misclassified or have large prediction errors by giving them more weight in subsequent samples. With each iteration, single tree models improve, focusing on difficult cases. While boosting enhances accuracy, it is computationally expensive, more prone to overfitting, and does not support parallel tree development. Random forests extend the bagging strategy by introducing greater diversity among trees. In addition to sampling the data with replacement, random forests randomly select a subset of predictor variables for each tree. This is particularly beneficial when predictor variables are highly correlated, as it reduces the correlation among trees and lowers the variance of prediction errors. A common guideline is to use the square root of the total number of predictor variables for each tree. Random forests are simple, computationally efficient, and provide feature importance information, helping you decide which predictor variables to prioritize or exclude. In summary, ensemble tree models combine the strengths of multiple decision trees to enhance accuracy, reduce overfitting, and improve stability. By leveraging techniques like bagging, boosting, and random forests, we can tailor ensemble methods to suit different types of data and prediction tasks. Let's move on to some practical examples to see these techniques in action. We can build boosting trees in JASP under the classification section of the Machine Learning tab. We will continue using the travel plan data file. We will use the same settings and variables that we used in building the classification tree in 13.2. Those settings are shown here. When we compare the accuracy of the boosting model with our original classification tree, we can see that the original model had a better accuracy rate when the same model parameters are retained. We can also build random forest trees in JASP under the classification section of the Machine Learning tab. We will continue using the travel plan data file. We will use the same settings and variables that we used in building the classification tree in 13.2. Those settings are shown here. When we compare the accuracy of the random forest model with our original classification tree, we can see that the original model had an equivalent accuracy rate when the same model parameters are retained. In light of these comparisons, we will stick to the classic classification decision tree for this course and all relevant assignments. Thank you for your attention. This concludes the lecture on ensemble trees.